So what are the level of the resolution of our example under phase equilibrium? So the data has been given to us as we have been given the mass of methanol, the mass of ethanol, the pure pressure of methanol, the pure pressure of ethanol. So we have to calculate A, the mole fractions, B, the partial pressures, C, the total pressure. But the first thing to do, you have to calculate the number of moles of each component in a mixture. So in this exercise, we need to have our calculator. It's very important because we're going to calculate. The first step is, so let's go to A, or 1, the mole fractions. So first of all, calculate the number of moles. Number of moles of methanol is given mass all over the molar mass. Given mass is 2.4 gram. Molar mass for methanol. Methanol is CH3OH. The carbon is 12 times 1 plus hydrogen is 1 times 3 plus 16 oxygen times 1 plus hydrogen 1 times 1. So for methanol, we have 32 gram per mole. Ethanol also have to calculate number. The ethanol is 12 times 2 plus 1 times 5, 16 times 1 plus 1 times 1 for hydrogen. In this case, I'm making use of the molar masses or the relative atomic masses. So for methanol or ethanol will be 46 gram per mole. So I have to punch here. So I have 2.4 divided by 32. I have 0.075 moles. So I calculate also the number of moles of ethanol, which is the given mass, molar mass. Given mass for ethanol 4.6 grams divided by 46. Number of mole of ethanol equals 4.6 divided by 46. So here we have 4.6 divided by 46. 0.1 mole. So given that we have the number of moles now, we can calculate peacefully. Let's calculate the total first of all. N total equals to N of methanol plus N of ethanol. N total equals to. So add the two number of moles. 0.075 plus 0.1. So we have 0.175 mole. So we're going on to calculating the mole fractions. Calculating the mole fraction. X of methanol is the number of mole of methanol divided by N total. 0.075 divided by 0.175. X of methanol equals 0.075 divided by 175 equals to 0.43. X of ethanol is N of ethanol divided by N theta. Ethanol is 0.1 divided by the total 0.175. X of ethanol equals to, so do the division. 0.1 divided by 0.175. 0.53. So in this case, they will have the mole fraction X of methanol, that is it, in the board. X of ethanol will have that in the board. But remember, the mole fraction of methanol is the number of moles of methanol divided by the total number of moles. The mole fraction of ethanol is the number of moles of ethanol divided by the total number of moles. So we have successfully calculated the mole fraction of the various components in the mixture. So we can go down to 2. 2 is their partial pressure. So I have to go to 2. But remember that when this type of exercise is given to you, the first step, first of all, you calculate the number of moles of each component in the mixture. Number of moles is given mass by the molar mass. By so doing, you have the number of moles of methanol. You have also the number of moles of ethanol. You calculate the total number of moles. That's the total number of moles. Then after calculating the total number of moles, you calculate the mole fraction of methanol in the mixture. You calculate the mole fraction of ethanol in the mixture. So I've calculated the mole fractions. Then let's go now to the partial pressures. Partial pressures. So partial pressures. That's beautiful. Partial pressures. So let's the partial pressure of methanol is the mole fraction of methanol times the pure pressure of methanol. The partial pressure of ethanol is the mole fraction of ethanol times the pure pressure of ethanol. That's beautiful. So now we are going to calculate them. So yes, P of methanol is X of methanol. So we have to know X of methanol. So X of methanol was 0.43 times 810 kilopascal. P of ethanol was 0.53 times 450 kilopascal. Remember that P theta have been given to us. P theta of methanol in the equation is 810 kilopascal. P theta of ethanol was 450 kilopascal. So these are the pure pressure. The pure pressure are given in the equation. So they are always given the equation. So given that they have been given, so we make use of it such that the pure pressure of methanol is the mole fraction of methanol times the pure pressure of methanol. The partial pressure, so the partial pressure of methanol is the mole fraction of methanol times the pure pressure. Also, we can have also the partial pressure of ethanol is the mole fraction of ethanol times the pure pressure of ethanol. So we have to punch on the calculator. So punching. So pure pressure of methanol equals to 0.43 times 810 equals to 348.3 kilopascal. Pure pressure of ethanol equals to 0.53 times 450 equals to 238.5 kilopascal. So we can now go to the last one, the total pressure. P total is equals to P of ethanol plus P of ethanol. P total, we're adding 348.3 plus 238.5. The total pressure equals 348.3 plus 238.5. So we have 586.8 kilopascal. So that's our total pressure. So now we're going, this is what ideal solution. So ideal solution are usually solutions or mixtures in which the component are successive member of the same homologous series, like a mixture of methanol and ethanol. All of them, they are alcohols. So in that case, we are going to talk about ideal mixture. The mixture of the same homologous series, the component of the same homologous series, the component have similar chemical and chemical property because they have the same functional group. So the components have similar intermolecular forces. In this case, in ethanol or alcohols, the intermolecular forces are hydrogen bondings. Such mixtures, they are ideal mixture. An ideal mixture is simply a mixture in which the components of the mixture have similar chemical and intermolecular structure. In this case, we can also have non-ideal mixture because here our topic was ideal mixture and Raoult's law. We also have non-ideal mixture. These are mixtures that deviate from Raoult's law. It can be positive deviation or negative deviation. But we are going to start with positive deviation. So let's now see non-ideal mixtures. Non-ideal mixtures. Non-ideal mixture. Non-ideal mixtures. One. Positive deviation. Positive deviation. So, if a mixture deviates positively in Raoult's law, it simply means that the vapor pressure is higher than that predicted by Raoult's law. We can have an example of water and ethanol. So, I have an example of water and ethanol. So, in this case, we have a non-ideal mixture. The components in this case, there's water, there's ethanol. Then we have to identify the intermolecular forces in these two components. In water, we have hydrogen bondings. So that's how water is, H2O. So water has two hydrogen bonds. Ethanol, we have one hydrogen bond. So I have two hydrogen bonds for water. Ethanol will have one hydrogen bond. So the intermolecular force in water is more pronounced than in alcohol or ethanol. So given that the intermolecular force in water is more pronounced than ethanol, the vapor pressure of ethanol will be higher than that of water. So upon mixing these two components, the bonds are broken. The molecules have high tendency to vaporize or to turn into vapor. By turning into vapor, they form a vapor on top of the liquid. So in this case, for positive deviation, we can say the vapor pressure is higher than that predicted by Raoult. This can be illustrated on the vapor pressure composition diagram below. So let me have the vapor pressure composition diagram. So we said hydrogen bonds have strong ethanol and water has strong intermolecular forces. But the one in water is more pronounced than the one in ethanol, meaning the vapor pressure of water is higher than that of ethanol. So here we have water, P theta of water. Here we have P theta of ethanol. Ethanol is an alcohol. Vapor pressure. Vapor pressure. Composition. 100%. 100% ethanol. 100% water. So we join the two. But remember that this component, this mixture deviate positively from Raoult's law. So for positive deviation, the vapor pressure is higher than that predicted by Raoult's law. So we have curves. Here we have curves. Here we have curves. Here we have curves. So here we can have the vapor pressure of water. You have the vapor pressure of ethanol. So that's the vapor pressure composition diagram for a mixture that deviates positively from Raoult's law. So positive deviation, you have a curve-like structure showing that the vapor pressure is higher than that predicted by Raoult's law. So for positive deviation to occur, one or two of the components will have hydrogen bondings. So the hydrogen bonds upon mixing are being broken down. So the hydrogen bonds are being broken down. Once the hydrogen bonds are broken, the vapor pressure is higher than that predicted by Raoult's law. So this is the case of positive deviation. And this positive deviation has some consequences. Given that the bonds are being broken, the vapor pressure is higher than that predicted by Raoult's law. So the pressure of the mixture increases. So what about the temperature of the mixture? The temperature of the mixture drops because bonds are absorbed to break the bonds, or heat is absorbed to break the bond. That's why the temperature of the mixture will drop, because the reaction is an endothermic reaction. Heat is absorbed to break the hydrogen bondings in water and to also break the hydrogen bond in ethanol. So we'll have now an increase in volume. The volume will increase. Why? Because the hydrogen bonds are broken, the molecules are far away from each other. Because in positive deviation, there's what we call bond breaking. So bonds are being broken. And once bonds are broken, the volume of the mixture will automatically increase. So these are some consequences of positive deviation. Now we are going to move to negative deviation. But water and ethanol, these are not the only mixture that will have positive deviation. I told you that for us to have positive deviation, one of the components should have hydrogen bondings, or both even. Another type of mixture, we can have water and carbon disulfide, ethanol and carbon disulfide, ethanol and benzene. So these are some examples of mixture that deviate positively from Raoult's law. So let's now go to negative deviation. Negative deviation. Negative deviation. For mixture to deviate negatively from Raoult's law, the vapor pressure should be lower than that predicted by Raoult's law. So in this case, there's no more bond breaking, but there's bond formation. A typical example is a mixture of propanone and trichloromethane. So let's take an example. Propanone, which is a ketone. Propanone, which is a ketone, and trichloromethane. So the intermolecular forces, none of these components have hydrogen bondings. But when you mix them, hydrogen bonds will be formed. So let's take the case of propanone and trichloromethane. So let's say you mix the two guys. Cl, Cl, Cl. So when you mix the two components together, hydrogen bonds have been formed. The hydrogen bonds are formed between the oxygen of the keto compound and the hydrogen of the trichloromethane. So hydrogen bonds are formed, and for us to have hydrogen bond, hydrogen has to be bonded to fun. Fun in this case means oxygen, fluorine, or nitrogen. So bonds are being formed, meaning heat is released during bond formation. The temperature of the mixture will increase. So how does negative deviation come about? Upon mixing the two components, bonds are being formed. The molecules now are held by strong intermolecular forces. They are tied together. The tendency of them to vaporize or turn into vapor decrease. Hence, the vapor pressure is lower than that predicted by Raoult's law. But for us to know which one have a higher vapor pressure or a lower vapor pressure, we have to identify the intermolecular forces found in both. So, in this case, we have for ethanol, propanone, we have dipole-dipole attraction. Here also we have dipole-dipole attraction. Because this molecule can be represented like that. We have C, H, Cl, Cl, Cl. Sigma minus, sigma minus, sigma minus. You have 3 sigma plus. So the dipole-dipole attraction here is stronger than the one of keto. The keto is just like that. Sigma minus, sigma plus. So for the keto group like you have sigma minus, sigma plus. You have the dipole-dipole attraction, but here we have 3 dipole attraction. So we can draw the vapor pressure composition diagram. So draw the vapor pressure composition diagram. Composition. So 100% acetone. So yeah, 100% trichloromethane. So given that trichloromethane have 3 dipole-dipole attraction, the trichloromethane will be down here. I'll put P theta trichloromethane because the intermolecular forces in trichloromethane is more pronounced. Trichloromethane more pronounced than that in acetone. So acetone have just 1 dipole-dipole attraction, whilst trichloromethane has up to 3 dipole-dipole attraction. So the intermolecular force in trichloromethane is stronger than for acetone or propanone. Here we have a P theta of acetone. So acetone CH3. So this is what I was saying. So the vapor pressure is lower than that predicted by Raoult's law. So that's the difference between positive deviation. So here we have vapor pressure. So that's the difference between positive deviation and a negative deviation. For positive deviation, the curves verge upward. For negative deviation, the curve verge downward. So in this case, we have a negative deviation. So for negative deviation, the vapor pressure is lower than that predicted by Raoult's law. So negative deviation also have consequences. The consequences here are: 1. The vapor pressure is lower than that predicted by Raoult's law. 2. The temperature of the mixture increases because energy is released during bond formation. Here bonds are being formed, so hydrogen bonds are formed. During bond formation, heat is released. And when heat is released, the temperature of the mixture increases. So apart from the temperature of the mixture being increasing, we can also have the temperature. We spoke about the temperature. So what about the volume? Strong intermolecular forces are formed. Their mixture are now held together by strong forces. The volume of the mixture drops. So in that case, we've arrived at the end of this our first topic, our topic 1, which is phase equilibrium. So we'll go straight to our topic 2, which is acid-base equilibrium. So thank you for watching. Follow me on education.